So we're moving into the last part of this chapter dealing with one-dimensional steady-state conduction. We're moving into the section on extended surfaces. Sometimes you hear the word, what? What is an extended surface? Extended surfaces are more than just fins, but fins are a large part of the analysis, what we call extended surfaces. Okay? So if you really want to just replace it with something that you may be more familiar with, say, oh, we're going to study fins. Okay. Well, we're going to spend a lot of time studying fins. We won't finish it all today. When you look ahead, this section 3.7, bio-heat equation, I'm not going to cover it. It's just a little extra beyond the scope of this class. Thermoelectric power generation, not going to cover it. Micro and nanoscale conduction, not going to cover it. So those are all worthwhile topics. It's just we don't have time. So we're going to really emphasize section 3.6, heat transfer from extended surfaces. What do you see here? What is this right here? Radiator. Where would you find one? Automobile in the front to provide cooling. What goes through the inside of the radiator? Primarily water with a little ethylene glycol to keep it from freezing. Right? Little antifreeze. Primarily water, a liquid. What goes across the outside? Air. Let's take a look here. What do you see? Condenser in an air conditioning system, usually on the outside of the house. It's a coil, right? And so that's going to, the refrigerant that's going inside is going to condense. What goes across the outside? Air. What's right here? The A coil. That's the evaporator in an air conditioning system, typically in the inside of the house. So what's happening inside, it's a refrigerant that's boiling or evaporating. And about over the outside of the coils, what's happening? Air's coming up and then going across like that and across like that in the duct system. And so it's air on the outside. This would be a flat coil, evaporator coil. Not all evaporator coils are A coils. Most of them, or a lot of them are, but they're different shapes and geometries. Okay. What do you see? Do you see the fins? Do you see the fins? I know I don't have blown up anything, but basically you have fluid passage through, and then often you have some material that goes. What's that material doing? Holding it such that the tubes that the fluid goes through? No, it's promoting heat transfer. It's primarily to promote heat transfer, not providing stiffness or rigidity to the system. Similarly here, there's all kinds of fins that different companies have. Often you take your finger and rake it across there, right? And you just bent all the fins. They're easy to bend. Don't do it, right? You should straighten them out with a fin comb to straighten out your fins so you promote good heat transfer. Similarly here, it's a finned surface. You as a thermal engineer want to promote the rate of heat transfer. You need to reject some heat. You need to reject it to ambient air or somewhere to promote heat transfer to air. So you want a large Q. That's what you want. You want a large Q, rate of heat transfer. How can you achieve it? You can think of three things that affect it. The delta T. Make a large delta T. How do you make a large delta T? Either you put a hot surface or a cold fluid. Well, a lot of times we have to dump to air, the ambient air, and it's just what it is. In the summer, if your air conditioning system for your house or your automobile needs to work, or your radiator needs to reject heat to the air, it's a hot day out there, and you still don't want to overheat that engine, true? So often this is fixed. You can't play with it too much. Often this is fixed. You don't want to overheat. Okay? So the delta T you can only boost so much. What about H? What do we know about H? If I want to promote heat transfer, dumping it to air, what do I know about H? What should I do to the air to help promote the heat transfer? Get it to flow forced over the surface with a high speed, right? To promote a higher convection coefficient. If I increase the velocity, I increase maybe something like turbulence or mixing, ripping into that boundary layer. A lot of those concepts were introduced in Chapter 1, and it promotes a high H. What also could you do? Increase the area. And that's what fins do. This is what fins do. They increase the area that the fluid's in contact with. Let's ask this question, a clicker question. Is it harder to have a large Q? Remind me, what was Q again? Rate of heat transfer. I want a lot of watts. Watts, that's the units for rate of heat transfer. It is harder to have a large Q into blank compared to blank. Into air compared to water, water compared to air, air into a vacuum, water into a vacuum. I'll give you a few minutes here to answer. Not a few minutes, a few seconds. All right, everybody in? So I know this is a difficult wording, but the comma and the way it's worded is it true that everything over here is hard to dump the heat into compared to over on the second after the comma is easier? That's really what it's saying. It is harder to have a large heat transfer into blank than to blank, meaning this is easier. This is easier, right? So you just kind of say to yourself, is it harder to dump the heat into air compared to water? Is water easier than air? The answer is A. Water, is it harder to dump heat into water compared to air? Is that true? Then the answer would be B. Is it easier to dump heat into air than it is to dump the heat into a vacuum? Is it easier to dump heat into water compared that it would be easier to dump into a vacuum? Is the vacuum easy compared to water? Is the vacuum easy compared to air? Does that make sense? I know the wording is difficult. I tried to reword this a couple times and I failed, but the idea is I want to get across. Most of you caught it. It's right. Air, it's harder to dump heat into air than the water. And it's easier to dump it into air or water than into a vacuum. A vacuum has nothing but radiation to take it away. So that's really hard to dump it in. Why is it harder to convect heat from a hot surface into air than from a hot surface into water? Why? Well, air can't move as fast as water. Answer A. Density difference, heat capacity difference, thermal conductivity difference. Or I don't agree with that statement. The statement's incorrect. It's just the opposite. So we're running the clicker. We'll give you about 60 seconds. All right, everybody in? So let's go ahead and stop and then answer this one. So it's harder to convect heat from a hot surface into air than water because air can't move as fast. You can make air move fast. Density, is that it? Specific heat, is that it? Heat capacity? How about the thermal conductivity? Isn't that it? So isn't D that right answer? It's harder to convect heat into air. If we go back and we take a look at what we said in the introduction, we talked about diffusion of heat or conduction of heat is really a diffusion mechanism. True? Bouncing, pushing against each other in a solid, liquid, vibrating or sliding and bouncing, or even a gas moving and then through primarily a vacuum, then striking each other. Okay, but it's a diffusion of molecular energy from higher to lower energy zones, from higher temperature to lower. What is convection? Convection was two things. It was the diffusion of heat, conduction, and it was advection of heat, meaning once I got it into the fluid, it was swept away. And that's a really efficient way to move heat from one zone to another zone. Put hot fluid in a pipe and you can transport that fluid a long way. Put cold fluid in a pipe, you can transport that fluid a long way. So convection is diffusion or conduction and advection. The hard part is getting it from that hot surface, think about it that way, into the cooler fluid so it can get swept away. What do we know about no-slipped boundary conditions from fluid mechanics? How fast is the fluid flowing that's immediately adjacent to the solid? It's not flowing. So how does it get through that stagnant layer of fluid? It can be very, very small stagnant layer of fluid, especially if the fluid flow is turbulent. It's ripping it up and chewing it up. But it's really that zone right there often controls it. It has to be through diffusion or conduction to get it in there. It's a combination. Convection's conduction with advection. So what do I have covered up under this box? At around 300 Kelvin, let's compare two fluids, air and water, liquid water. Look at the thermal conductivity. Seem reasonable, 0.0263. Water, 0.6. That's over 20 times greater than air, the thermal conductivity of water. That's why, one of the major reasons that it's easier to get the energy into the fluid known as water versus air. Your convection coefficients are going to be larger in water because the conductivity of water is high. Okay, did we grade this one? Yeah, we did grade it. So now we want to talk about extended surfaces, and we're going to be interested in predicting how to promote heat transfer from, let's start off with a base something, and we're going to say we're going to attach something to this. We're going to attach something that is round, that protrudes out from that surface, perpendicular out into a fluid that could be flowing. So that would be a round pin fin. So it's a pin fin. Or you could think about having a surface, and you could attach a pin, a fin that looks like this. What does that look like? It's a rectangular fin. Now I know the book starts with varying cross-sectional areas. Let's make it easy for ourselves as introductory purpose. For introductory purposes, let's just consider the cross-sectional area of the fin as constant. It's not narrowing down or expanding. It's constant as you move further away from the surface. So we introduce a coordinate system, x. X goes between 0 at the base and L at the tip. So we talk about the base of the fin and the tip of the fin. And if you attach it to a surface that's all at this TB, then the base of the fin is at that temperature TB. Why did they put a B on that temperature? Temperature of the base. Okay. Now if you wanted to, you could plot as a function of x going from 0 to L the temperature profile in that fin. The highest it would be is TB. If you're surrounding the fin with some fluid, right? The fluid is characterized by a convection coefficient as well as T infinity. What does T infinity stand for? The temperature of the fluid far away from the hot surface. Something that's an infinity. Okay. So let's put that we have a hot fin, and so here is T infinity. What does the temperature profile look like in a fin? Well, it could look in a lot of different ways. It could look something like this, where it just goes down and stops. It could look something like this. It could look something like this, where in case A, how would you characterize it? I would say the fin is almost the same temperature everywhere. It's isothermal. So it must be easy to transfer heat in conduction down that fin. The hard part is getting it off into the fluid. How about for B? Well, it's being conducted, and then it's actually a lot of it's being transported as it's being conducted down the length of that fin into the fluid, and then the temperature of the fin is dropping. And so the temperature at the tip is lower than the temperature of the base. How about case C? It dropped a lot. Most of the fin is at what temperature? More than half. It looks like half of the fin, if not more, is at the fluid temperature. Is it transferring any more heat in that second half of the fin for KC? No, it's not. So that KC would think, well, it's easy to move the heat off of it into the fluid and hard to move it down the length. So probably the thermal conductivity of the rod is low for KC. Make sense? Well, the goal is to develop an equation, a mathematical equation, so we could predict the temperature distribution in the length of the fin, and then predict the rate of heat transfer through the fin. How do we do that? Well, I'm going to just do it for the pin fin, and then it's a similar setup for the rectangular fin. Let's do this for both of them. This is the area that heat is conducted down the length of the fin. That area is A sub C. It's this area for the rectangle fin, A sub C. For the rectangular fin of length L, moving out from the base, of width W, and of thickness T, can you tell me what the cross-sectional area is? Is it the product of W times T? Yeah. All right. Go back to our pin fin. What is the cross-sectional area? Pi r squared or pi d squared over 4. If you like radius or diameter, both are acceptable. There's another parameter we're going to use in the derivation, not just the cross-sectional area, but we're going to use P. P is not pressure, it's perimeter. Perimeter. So for this pin fin, what would be the perimeter? 2 pi cap r or pi d, either one. What would be the perimeter for the rectangular fin? 2w plus 2t. And if the t's are very small compared to the w's, you could probably just neglect the 2t and just call it 2w. But it's 2w plus 2t. All right, now we're ready to set it up. What we do is we grab a little element. I'm going to try and grab it over here. And we're going to talk about a heat balance for that little element. That little element as length delta x. It starts at the location x and ends at the location x plus delta x. So its thickness is delta x. And we have heat transfer coming from the base that way. And so this is Q at x. That's coming into my little element. The heat transfer by conduction is going out at Q at x plus delta x. It's still in the x direction, but it's a little further down the length of that pin fin. What other heat transfer do we have? We have the convection coming off, Q convection. So I have one in, two outs. I have Qx in equal to Qx plus delta x plus Q convection out. Isn't that a good energy balance? Steady state, energy is conserved. That's my energy balance. I'll move this one over. Negative Q sub x plus delta x plus Q sub x is equal to Q. I'm doing the minor steps in the algebra. Now we substitute. We say, you know what? I know how to develop a relationship for the heat flux at the location x plus delta x. That's minus K A sub C, sorry, not the heat flux, but the heat transfer rate. That's why I multiply by AC times dt dx at x plus delta x. True? And then we say also it's plus a Q sub x, which is minus K A sub C dt dx at x. So I used Fourier's law twice. Once at x plus delta x and once at x. This one needs to have that minus sign come down. And when you have that minus sign come down, this turns it into a positive in front. Right? And this one has a negative in front of it for the second term. Okay, that's equal to H times the area for convection. The area for convection is the perimeter times delta x, the length. P dx gives me that area for convection. And the temperature difference, T at that location, minus T infinity. Professor, I think the heat transfer is two-dimensional in this pin fin. I know it is, but we're neglecting the heat transfer 2D. We're approximating it as 1D. What's the temperature difference between the temperature at the center line of that fin anywhere along it and the radius, the outer radius, anywhere along it? Just compare here and here. Well, it's small compared to the temperature difference axially down the fin. That's why it's one-dimensional. So for every cross section, we only talk about one temperature. That temperature is only a function of x, not a function of x and r. Subtle point, but there you go. So what do? We take and divide by Ka sub c to get these over. Divide by the delta x to get that one over. And what do I do with this quotient? We think about the limit as delta x goes to 0. And from calculus, you're experts in calculus, you recall, that's just the derivative. But it's a derivative of a derivative, so it's hard to see it sometimes. But a derivative of a derivative is a second derivative. So what we end up with is a differential equation, which is the second derivative of temperature with respect to space, equal to P over Ka sub c times T minus T infinity. Sometimes they'll write it with introducing m squared is HP over Ka sub c. And sometimes they'll put everything on one side and put a 0 on the equal sign. And you'll have the second derivative of temperature with respect to x squared minus m squared T minus T infinity. This is, I think, the form the book puts it out to you. It's because now what you're going to do is you're going to say, oh, I took a whole class studying how to solve ordinary differential equations. This is second order, so I need two boundary conditions. And then I would have my strategy from another class to employ to solve this equation. Let's talk about the first boundary condition number 1, which would be the temperature maybe at the base at x equal to 0. Well, it's the specified temperature, TB. What about the other boundary condition? You could have 3 choices. Convection, boundary condition off the tip, specified temperature boundary condition off the tip, or insulated tip. The insulated tip is mathematically a lot easier. All 3 are given and worked out in the textbook, but the one that's easier to use for us in this class as well, and they'll justify why we use it, is the insulated tip. So the second boundary condition is dt dx at x equal to L is equal to 0. Professor, don't you have some convection off of the end? Yes, you do, and we'll correct for that in a second. Now I have that. I have my differential equation and 2 boundary conditions. You can now separate, integrate, or try another strategy for solving this one. This one's not going to go so easily in separate and integrate. It's going to go by a technique known as guess the form and see if it works. Go look in your differential equations book. There's something described like that. It's like, just try this form and see if it works. So when you try the form, you're going to find that you're going to come up with some lovely functions that you haven't seen in a while, but they're your old friends. Sinh, cosh, and the hyperbolic tangent. The hyperbolic sines and cosines. All right? This is the definition of the sinh and the cosh and the hyperbolic tangent. And you can go and review from Wikipedia about your cinches and coshes and hyperbolic tangents, because that's what comes out. And if you start to account for certain selected fins that have changing cross-sectional area, you'll start getting Bessel functions. Not in this class. Okay? The hardest thing we're going to do is these hyperbolic sinh, cosh, and tangent. So let's do a quick reminder. I can't remember, what does the plot of the sinh or the cosh or the hyperbolic tangent look like? I would say just try Wolfram alpha, and you can quickly plot things. Here's a plot of the hyperbolic tangent. It starts at 0, and for large x, all I'm doing is plotting the hyperbolic tangent of x. What does it do? It goes near 1. And then what is the cinch? It starts at 0 and goes off to positive infinity. What about the cosh? The cosh starts at 1 and stays slightly ahead of the hyperbolic cinch. Those are our functions. Now, here's a table with a lot of the results. They not only solved it for the convective boundary condition, the prescribed temperature boundary condition, and an infinitely long case, but the case that I want to emphasize, which is this one, the adiabatic tip, the insulated tip. So what did they show here? Well, they're showing you the solution, which is theta divided by theta b. Well, what was theta? It's the temperature difference defined right here. T minus T infinity divided by the base temperature, TB, minus T infinity. So it's equal to the cosh of m times L minus x divided by the cosh of ml. Well, what was that m again? That was our parameter. So m squared is hp over kac. That gives us the temperature distribution, doesn't it? The next thing of importance is our heat transfer rate from the fin. So what goes down the fin eventually gets into the fluid? You can calculate that by taking minus the k of the fin, a sub c, times dt dx evaluated at x equal to 0. It's how much conducted gets into the fin. It's eventually going to be convected off. If you take that analytic solution for the temperature profile, stick it in there, work the math, you'll get that for this adiabatic, you get the Q fin equal to cap m, a new parameter defined right here, times the hyperbolic tangent of ml. Are these equations in the equation sheet? Anybody look? Probably want to send her an email and encourage her to put them in. Right? They're in the table. I wouldn't put all the table in, or maybe I don't know if she can do that. She's pretty good. But anyway, that's every term that's defined here. True? Okay, what is theta b again? Theta b is that temperature difference evaluated at the base, so TB minus T infinity. Let's explore then this equation, which is for the rate of heat transfer that's going to get into the fin, which then is off of the fin into the fluid. Group of parameters, temperature difference to hyperbolic tangent of m and L sub c. I'll talk about L sub c in a second. But if you plot this function, what you find is that as you increase the m L sub c, this is the x-axis, which is treated as m L sub c, the k and the h and the p and the a sub c doesn't change, and the theta b doesn't change, but the rate of heat transfer changes as m L sub c increases. But what about the hyperbolic tangent? What does that function do? It maxes out at 1. So if you continue to extend and make your physical fin longer and longer and longer, you won't necessarily get more watts into the fluid, from the surface into the fluid. So you say, well, how long is long enough? Well, if you wanted to move 99%, you put in hyperbolic tangent x equal to 99 and let it solve for it, you'll find that this comes in around 2.65. Which means 99% of the maximum possible heat transfer rate is achieved for ml equal to 2.65. There's no reason to make L greater than 2.65 divided by m. That's actually pretty ridiculous to get that long anyway. Can you see that? Somebody says, well, that's 99%. How about if we just push off 98%? Well, then 98% comes in at 2.3. So it would be around right there, 2.3. So whatever your criteria is, you say, maybe I want 95%. Well, it's not going to be 2.65. It's not going to be 2.3. It's going to be shorter. So don't make super long fins. This shows you how long is kind of, you're getting to the limit of being ridiculously long physically. Yes, sir, you had a question?
No, so just an answer. These are not on the equation sheet.
Okay, we'll send her an email. Don't text her. All right. So this helps a design engineer make some good choices in the fin. Yes, sir.
I was just thinking, I mean, I guess it doesn't, but how would you account for radiation of the fin, say?
Not in these equations, right. And often the radiation, it can be important, especially if it's a hot fin. But it will augment, which is usually good because you're trying to reject heat. It'll just be a bonus, so to speak, for the design engineer. But if you wanted to, you would have to go to a more detailed numerical analysis, accounting for that t to the fourth. That's not going to go. The analytic techniques just don't solve problems readily that are nonlinear like that. Well, there's two parameters that make sense. You just have to say what exactly is defined in the literature considering fin performance. Well, one is called the fin effectiveness. What is it? Here it is, the symbol, fin effectiveness. It's the ratio of the fin heat transfer rate, what is actually going through the fin. We just did that for one of our cases, Q sub F, divided by what it would be if you didn't have any fin, but it was just a bare surface of the base exposed. Well, then it would just be your old equation for Q bare is just the H times the area bare, which is the cross-sectional area at the base, times theta B. So you need probably at least a factor of 2, or you're not going to get very excited about finning that surface, are you? If you put a fin on there and the fin effectiveness comes in at 1.2, that's a big yawn. It's like, well, put a lot of work into it and I got a 20% increase. No. I need at least a doubling. I need to be, 2 for the fin effectiveness or more. Okay? The other parameter is a fin efficiency. What is that defined as? First of all, here's the symbol for the fin efficiency. It's the same numerator, how much heat is transferred, but not compared to a base without any fin attached, but compared to the maximum possible if you made some super expensive fin with the ultra high thermal conductivity. If you had an ultra high thermal conductivity material, what would the temperature everywhere down that fin look like? It would be T base. And so they said, well, compare that, make that comparison. So everywhere it's equal to T base. And this area is not the cross-sectional area, but it's the area of the fin. This one, if it's a round one, it'd be perimeter, well, even square. Perimeter times L, wouldn't it? Neglecting what's on the tip. Just that's the convective off the side. That'd be the area of the fin. So what about this fin efficiency? Well, you'd like it to be high, but, well, it's another metric. Okay. Now you say we use that very simple analysis for the insulated tip. We'll do this. As an engineer or budding engineer, this should really appeal to you. We know the physical length is this, but in our equations, treat the physical length as being extended a little bit, corrected. It's like taking that rectangular fin, right? And we're going to extend it a little bit. How much? We'll cut this in half and flip this side up, and that would be going out an additional T over 2 on the top. Flip that side down, that would be going out an additional T over 2 on the bottom. So use a corrected length in the equations, which for a rectangular fin extends the physical length by T over 2. Did that make sense? And now treat that new end as truly being insulated. And the book talks about how accurate that approximation is, and it's good. What about for the round? Well, it's a little harder to kind of see it cutting and flipping out, but extend this by d over 4, not d over 2, d over 4, and that'll be a corrected length. So when you use the equation to calculate, what is QF again? The rate of heat transfer off of that fin. Use the corrected length. The fin effectiveness, or efficiency and effectiveness, etc. Here is our M. M is a parameter used in these equations, lowercase m, and then cap M. All right. All right, that's where I wanted to stop. So let's go ahead and stop for today.